So as climate change creates more frequent, more unpredictable, and more intense storm events, ones that we can't gauge, there's the ways that we've been measuring the intensity of storms is completely out of whack with the way that we've been seeing these storms evolve over the last 5 to 10 years. So you've got so much water coming into the system. So the ability of a city's infrastructure to thrive under those additional pressures, that's the idea of resiliency. But in order for us to really adapt and really play into and understand what a true solution to a true 2050 problem might look like, it's got to be a lot more creative than I think it's been. And I think we're not giving ourselves enough time to come up with more well-rounded solutions that might take into account the things that we can't predict. You've got sewer overflows occurring, you've got basement backups occurring, so you've got water in places that you don't want it. And at the end of the day, we're still applying these 1980s solutions to these 2050 problems.
Hey, Paige, thanks so much for joining me today. I really appreciate it.
Thanks, Jack. Happy to be here.
So tell us a little bit about yourself.
Sure. Paige Peters, founder and CTO of Rapid Radicals Technology. Also just resident water engineer. Happy to talk about anything related to water and bombard people in random settings with conversations and facts about water and wastewater. But I've been working in the water space essentially since I started my graduate degree at Marquette University. And just last May, I finished my PhD in civil environmental engineering. While I was at Marquette working on my PhD is when I founded Rapid Radicals. I spent a long time looking at the technical, the scientific, and the social business side of bringing our wastewater technology to the world, but understanding how that tech fits in with our existing infrastructure along the way.
I want to start off a bit of a broad question because I'm really interested in your perspective. The water industry is under a bit of heat on a global scale. We're finding that the water industry is increasingly in the front page of the newspapers and everything. And it's obviously the sector that you and I both very much know and love. I'd love to maybe start off with just your perspective on what is the current state of water infrastructure?
What a large question to pose at the onset, but I think it's an important question that we should all be thinking about, whether you work in the water industry or not, because it is obviously a sector that impacts every single one of us, especially those of us who live in cities. So when I think about infrastructure, water infrastructure, drinking water, wastewater, stormwater, it's this combination of the conveyance system, so that which comes from our houses, our buildings, our offices, and essentially centrally conveys those to a centralized treatment plant. And there's lots of infrastructure among all of that. But the challenge is that it is a chronically underinvested in infrastructure, where the value that we place on it in terms of how much we're willing to spend on it is incredibly disproportionate to how much we rely on it. And a lot of our infrastructure in many large cities has been in place for over 100 years and has very minimally been taken care of in the meantime. So there's lots of broken pipes, there's lots of pieces of our centralized infrastructure that need improvements for energy efficiency, an update and for innovation, a increasing capacity to deal with increasing population, increasing urbanization, and aging infrastructure. So the state of it is ultimately, as I said, this chronic underinvestment, while we're continuing to place this great value on it by saying, move into cities, here's where you can get great jobs, you have culture, you can have community. But as more people come in, we need to be creating a more valuable or a more reliable infrastructure. So when I think about the state of it, it's not just physically, what's the American Society for Civil Engineers rating American infrastructure, other infrastructures around the world. It's what's the state of our interpretation, our perspective, and how much we're willing to invest in this thing that we're giving this great value to.
You spoke a little bit about chronic underinvestment. I guess chronic underinvestment is determined by the demands and the pressures put on the water infrastructure. What sort of pressures do you see on the infrastructure that we are so heavily reliant upon today?
Mm-hmm. Yeah, whenever the high level perspective of it is the reality of climate change creating new pressures, physical, literal, figurative, whatever you want to say, related to too much water trying to be conveyed through our existing infrastructures to these centralized plants, still treating them to permit and releasing them into our waterways. So as climate change creates more frequent, more unpredictable, and more intense storm events, ones that we can't gauge, there's the ways that we've been measuring the intensity of storms is completely out of whack with the way that we've been seeing these storms evolve over the last 5 to 10 years. As climate change creates these new pressures, and we have this old system that was built to solve the problems of the last century, not the problems of the future century, this need to look at the way that we're solving these problems differently is so pressing. So you've got so much water coming into the system, you've got sewer overflows occurring, you've got basement backups occurring, so you've got water in places that you don't want it. And at the end of the day, we're still applying these 1980s solutions to these 2050 problems.
It's a really interesting idea there. So applying 1980 solutions to 2050 problems. So the 2050 reference, I assume, is the horizon of which the water industry plan for. So today we look ahead and say, hey, what are our infrastructure needs down the line as far as 2050? And we then invest and spend. So then the assets are operational. So we're almost ahead of the game.
Yeah, in the US, we've been developing 2050 facilities plans for decades. And that's saying that we want our infrastructure, we want to be able to anticipate what our infrastructure needs are going to be like in the year 2050. Obviously, and it's all modeled based on what we've known in the past, what we've known in the last decade. But as we're seeing these rapid changes in our climate that is directly impacting this existing infrastructure, I'm curious and uncertain as to how well those plans are taking into account all of these changes that we're seeing. It's not an easy feat by any means, but to build incredible, and I'm going to use the word resilience, but I want to define it quickly as well. So that's a buzzword that we throw around all the time within the place that within the industry right now, especially related to climate change. How do we build more resilient infrastructure? And I like to use the definition of alkalinity to play off of to build our definition of resilience, which is the ability of an infrastructure to thrive under the pressures added from climate change or other infrastructure, population, any other factors. So the ability of a city's infrastructure to thrive under those additional pressures. That's the idea of resiliency. But in order for us to really adapt and really play into and understand what a true solution to a true 2050 problem might look like, it's got to be a lot more creative than I think it's been. And I think we're not giving ourselves enough time to come up with more well-rounded solutions that might take into account the things that we can't predict. But now we have more information to at least have an idea of either how bad it could be or how bad it's been and what the results are, and taking that, iterating it, and then extrapolating that into our 2050s plans.
So that period, 1980 to 2050, large period, we know that because of climate change, the weather has dramatically changed over that period, a lot more erratic. I am keen to talk to you about what those sort of 2050 solutions look like. But I guess just before we do that, I'd love to really just drill down into how much of an impact that change in weather has on our water infrastructure. Why isn't our water infrastructure network able to support these new weather patterns that we're seeing today?
When I reference this 1980s solution, in a big way, when we first, in the United States, I'll speak specifically to the United States, when we first started seeing these challenges with sewer overflows and with excess water in especially our combined sewer systems where you're conveying stormwater and sanitary sewage in the same pipe, when we really in the US started seeing issues with that was around the 1980s. And the solution at the time was, let's just build more tunnels. Let's build underground storage tunnels. We'll store the water until the storm subsides, and then we'll pump and treat it at the wastewater treatment plant. And the idea of doing that makes sense in theory, but it's not really an adaptive strategy. I honestly would think of it as more of a Band-Aid, because you never know where the rain's going to fall. And the challenge is more so in the conveyance of water to that centralized location. So if their storage tank is your centralized location during a storm event, but you're still conveying water over a broken conveyance system and infrastructure, then the problem remains the same around basement backups and what those challenges can become. That's that sort of 1980s perspective that let's just build storage tunnels and we'll store and treat the water later. And the challenge with that too is that everything that we've understood about cities and population and aging infrastructure, we're now in 2024 and large cities are still building tunnels, and they take billions of dollars, they take years to build, and they're incredibly disruptive to the communities around them. There's obviously a place for them. They solve a lot of problems. You can reduce your overflows from, or your spills from 50 a year down to maybe 2 or 4, which is the case in Milwaukee. But a lot of these ones that are still getting built, you get towards the end of them being built, and there's already this conversation of, yeah, they're still not going to eliminate sewer overflows because storms have gotten worse, our infrastructure has not been invested in otherwise, and the population's increased by X%. Part of that problem is that the approach worked in the 1980s. We built a little bit of framework around the policy and the regulation of that in the US in the 1990s, and then we've just leaned on that for the last 30 years. In the meantime, all these other things are changing in our climate and in the way people move into cities, move around cities, how we connect our infrastructure and how we relate to it. And in that same vein, we've also got a centralized infrastructure. If we're talking about these 3 key pieces, the conveyance system, the storage system for some of these combined sewer cities for wet weather flows, and then you've still got your centralized treatment plant. The other challenge is that you've also got a centralized wastewater treatment plant that is, in many cases, still relying on a relatively old technology, which to some extent, it's the tried and true perspective. And we could talk in an entirely different conversation around risk aversion. It's obviously relevant to this conversation too, but there's still this pretty key piece around the fact that we're using a technology that has been tried and true, which is great, but there's still a lot of innovation that can happen in that point.
So let's dive into it. What does the typical approach to wastewater treatment look like?
Around 4 main stages of wastewater treatment. I'm going to do my best to make this as high level as possible, so anybody listening is going to know, oh, I understand it. I can picture what you're talking about. But again, this is at these centralized wastewater treatment facilities, and we're shifting the rhetoric around wastewater treatment plant to be water resource recovery facilities, which we can come back to in a little bit. But essentially, you've got these 4 key pieces. The first piece is what we would call preliminary treatment, where you've got lots of screens and other treatment options like grit removal to take out the really big things that wind up in our sewers, things that get flushed down the toilet that shouldn't, things that in a combined system especially get put into the rivers and make their way to the treatment plant that shouldn't. That would be like bikes, things that get flushed that shouldn't. That would be like condoms and tampons. And I'm naming names because it makes people uncomfortable, but it should, because we should all be thinking about it. But that first stage is meant to take out some of those big, what we would call inert solids and large things that really can't pass on the infrastructure of the rest of the treatment plant. So that's preliminary treatment. In your primary treatment stage, which is your next stop, you're going to get all those solids, for the most part, settled out. So you just make these big tanks, you give that water enough, what we would call quiet time, non-turbulent time for those solids to settle out. And then the water off the top of that goes into the next stage, which is secondary treatment. And that usually includes a biological treatment step. It can look like a lot of different things. A conventional system might include something called activated sludge, where the organics and the bacteria, rather the bacteria in that system, break down those organics. And as that then passes on to the settling step within that, because you're adding a lot of air to break down those organics so that those bacteria have fuel to break down the organics. That stirs the water up again. You go into the kind of B aspect of secondary treatment where that solids gets knocked out again. And then you've got relatively clean water. You've dealt with your solids, you've dealt in primary treatment, you've dealt with your organics and your nutrients in secondary treatment. And now that water then passes on to your disinfection step, which is the fourth piece. So typically the fourth stage of a conventional wastewater treatment plant train would be your disinfection. And in most cases, you're applying chlorine to disinfect that water. And then you then have to dechlorinate it so you don't have a chlorine-rich water going into natural waterways that could easily disrupt the aquatic species. And after that, and you have your discharge permit, so that water meets your discharge permit requirements, and it goes into a waterway. In some cases, you'll also have a polishing step before you discharge where you can take out micropollutants, use different technologies like that's more common in Europe, particularly Switzerland. And that's going to be driven by a regulation that's requiring the removal of micropollutants. And other opportunities and other design options for disinfection could be UV or ozone disinfection. There's lots of different ways to apply it, but it all kind of depends on what you need to use for your specific situation, based on space, based on permit requirements, based on what your water looks like coming in, and based on what you need your water to look like on the way out.
Just for full clarity, for maybe folks listening that come from the energy sector or transport or elsewhere, where does the water come from that enters this treatment process? And when it leaves the treatment process, where does it go? Does it become drinking water, or does it then just flow into rivers?
When the water enters a treatment plant, it's collected from the conveyance system. So one of those big pieces of infrastructure I keep talking about, that's going to come from our homes, our buildings, in combined systems. Obviously, that's got a combined sewage and stormwater infrastructure conveyance system already, but all that water gets driven to a central location. So you've essentially got smaller pipes coming off your homes, larger pipes to collect all that home sewage or combined sewage in the streets, and then goes into a larger pipe and a larger pipe until you get to the treatment plant where you've then collected all of that sewage from whatever service area that might be. Some cities have one centralized treatment plant, so you're collecting water from an entire city. In a lot of cases, that's a gravity-fed infrastructure with a few pumping stations on the way, but we're trying to reduce the energy used in the conveyance system and reduce remote infrastructure. That's all gravity-fed. And then when it leaves, it depends on what type of water it's being discharged into. If it's what we would consider a navigable water or recreational water, you have different requirements for disinfection to make sure that water, people can still swim in it. It's clean enough to swim in. There's not going to be E. coli concerns. So if that's like in Milwaukee, it gets discharged into Lake Michigan. And that's obviously a water that a lot of people can interact with in different ways. It's also the source of our drinking water. Now, our drinking water pulls from a mile out into Lake Michigan and then gets treated. So you've got a pretty large buffer from where, even though our wastewater meets permit, from where wastewater and our drinking water are put into and taken out of respectively. In some cases, that water just goes into, after it leaves the treatment plant, into something like a sanitary canal. That's sole purpose is to just convey treated wastewater away and maybe into another body where it gets diluted further. And in some cases, and obviously we're seeing that more and more now, is that you're having either indirect or direct reuse, whether it's potable or otherwise. For a city setting, it's likely some sort of a potable reuse system where that water can then go straight into a drinking water treatment train. You build redundancy into your treatment technologies for wastewater, redundancy into your treatment technologies for drinking water, and that water is able to be safely consumed. So it's a direct potable reuse. In other cases, you've got this buffer where it goes into a waterway and then gets pulled out shortly after for drinking water, where if it's a reuse perspective, you've still got that redundancy to ensure safe wastewater treatment and safe drinking water treatment.
You spoke before about design options. How do these treatment processes and solutions vary? Are they all consistent and vary slightly depending on the permits, or is there considerable variation within the way that the treatment process is designed?
For the most part, I should say there's a million different ways to solve the same problem or to solve similar problems. And when we look at opportunities for innovation within this space, whether we decide new technologies or new process. The choices that influence those different processes are related to, like I mentioned a little bit before, those decision factors can be related to size, to cost. There are some systems, especially from the biological treatment system. So most of the innovations or design decisions that we make within a conventional wastewater treatment plant are around the energy efficiency within that secondary treatment system. Right now, we add a lot of air for a biological process to proceed, but you can change the ways that you either apply air or the type of bacteria that are doing the hard work of breaking down those organics and removing those nutrients. So that, again, could be different processes, ones that save space, ones that use less energy. But when you're getting into different options, you still have to consider, can this system handle the population that I'm serving? You might have a few more options when you're dealing with a smaller utility or a smaller service area than when you have to be treating water for, let's say, the entire city of Chicago. And I'll say the Metropolitan Water Reclamation District of Chicago in the US has 7 treatment plants. So they divide and conquer a little bit, but for the most part, that's still serving a huge amount of people. So you have to keep all that in mind. And then there is still some decisions that can be made on the type of disinfection that you do. In most cases, it's required, but there's been a huge desire to push away from chlorination and dechlorination. We've learned a lot about what chlorine can do well, and especially how cost effective it can be, but there's a lot that it still can't do. And there's some challenges that it can create by forming carcinogens in the water that it treats. So we look at those design factors in the biological step and in the disinfection step so that we're saving money, saving energy, still meeting permit, but essentially trying to make systems that are responding and adapting to the changes that we're seeing that reflect the public that we serve.
And it sounds as though our thinking has really come along over the last couple of decades. We know around the sort of micropollutants becoming increasingly a priority within the treatment process because of the infiltration of forever chemicals, a topic which was discussed on a previous podcast. And we know also with energy, the treatment process is often makes up the majority of the carbon footprint for a water company. So it really is quite an energy demanding process. So being able to shift that over to a cleaner, lower carbon form of energy is a big priority. So it sounds though our thinking is really coming along with this. What hurdles do you think we're still faced with? And where do you see the biggest opportunity for innovation still within that treatment process?
There's always room for innovation, right? I see the opportunities for innovation really within biological step and that disinfection step. We've been doing something that's worked for a very long time. And for example, activated sludge, like I mentioned, is this conventional biological treatment step within wastewater. It was invented in the UK in the early 1900s. It came to Milwaukee, Wisconsin in the US in around the 1920s. And we've been applying that technology for over 100 years. And that Milwaukee was one of the first treatment plants to apply activated sludge in secondary treatment. And there's this great pride in that where we're from. But if you think that's one of the greatest innovations we've had in wastewater in the last 100 years, now 100 years later, what makes sense going forward? Energy efficiency is obviously a key piece. We're worried about energy in all sectors, especially civil sectors of our lives. How do we make energy efficiency? So how do we take that biological step that is typically a cost-effective application and make it more energy efficient? How do we recover nutrients? So we're obviously seeing a shortage of that. So the innovations that we're seeing within wastewater currently are a response, obviously, again, to the public that we serve. We're worried about energy. Let's make it more energy efficient. We're worried about where our nutrients are going and the effect that that's having on our environment. Not only do we need to be removing those nutrients in wastewater because it can be a prevalent source of them, but we can also recover them and reuse them. And we have that stewardship component to it. But there's still this piece of biological treatment that we have been holding on to for so long. And it's written into a lot of our requirements in terms of the regulatory perspective about what technologies you can implement. We know that biological treatment will get us to the point that we want to be from a treatment perspective for organics and for nutrients. And we know that for the most part, chlorine is going to get us to where we need to be from a disinfection perspective. But so much about our society has changed since we started applying those technologies. There's still a place for them in large centralized treatment plants. But there's also this opportunity to start thinking, if we need more capacity, but we're in an urban space, we don't have more space, how do we create technologies that take up less space? How do we adapt to the fact that you can get this water that comes so fast when it starts storming and starts raining? It falls anywhere in that conveyance system. It rushes to a treatment plant. It takes around 6 to 8 hours for water to get treated in that biological step, not to mention the 2 to 4 hours before it gets there in primary treatment, and not to mention the at least 30 minutes after to go through disinfection. But that's too much time for that much water to be treated, which means we have to start thinking, if we really are going to build these adaptive plants, maybe biological treatment isn't the only solution for our conventional treatment plants or our centralized treatment plants. Or maybe centralized treatment isn't the only solution for how we deal with wastewater and treating wastewater in our urban settings.
That's a really interesting point. Treatment sites are they're quite large, as you alluded to. They're very expensive to build. It's interesting to hear that 6-hour time allowance needed to actually be able to treat the water. What is the alternative?
Starting to get into the reality that when biological treatment can take that long, and what our treatment goals become when you've got so much water and the alternative is just discharging untreated water into our lakes, rivers, streams, oceans, or having it back up into people's basements. There's still an oxidation step, but instead we can look at how chemical oxidation can fit into that same role to remove those organics and combine the disinfection component with it. Because what you're essentially doing to organics, you often also do to your biological components, to the microbiology of the water. So if we've got the step that we've known is tried and true, I had someone describe biological treatment to me once as a security blanket we wrap ourselves in. We know it's going to work in a lot of ways, but it just takes time. It takes up space. And so if we can expand the perspective outside of just biological treatment towards chemical oxidation, where we have spent a lot of time within especially industrial settings demonstrating that you can efficiently break down organics, then it opens up a whole new world to say, if we can do what biological treatment does in 8 hours in less than 30 minutes, you're taking up significantly less space, but you're still meeting those requirements that you need to, especially when you just need excess capacity, especially when the other option is discharging that water without it being treated especially into a waterway that we interact in.
You referred to it as a safety blanket before. Safety blanket, it sounds very nice and comfortable, but it doesn't quite sound like this sort of big transformational shift that the industry so really requires. So being able to rip away that safety blanket and put in a more dynamic system sounds as though what we need. Does this mean that for more like metropolitan serving utility companies, they don't need the scale of infrastructure investment required? Or is it more that this is the level that we need to operate at, it's just that we're putting the wrong infrastructure into the ground?
If we rip away this security blanket, it forces you to think, what else? What other options do we have? What other technologies can we implement? How can we be creative with what we know works well and what we need to adapt to? And every time we talk about innovation within this space, it's just, there's no silver bullet. So by no means would I say, let's get rid of biological treatment. It serves a purpose, and it's also implemented in so many places. It's a capital investment that so many communities have already made, and we should protect and maintain that capital investment. But if we're looking to expand how much that capital investment can do, duplicating it at the same scale makes no sense. If you can make it more efficient and use your existing infrastructure more efficiently, that is a fantastic use of that existing investment. And if you need more capacity, looking in a different perspective instead of the same old, let's do more biological, let's build more aeration tanks, add more aeration capacity. There's this shift that we have to consider to supplementing our existing infrastructure with a technology that in other industries and applications has been tried and true to support the needs of the municipal space so that cities can have that extra capacity. When it comes to the investment that they're making, the square footprint goes down significantly just because that detention time goes down so much. The amount that you're trying to treat, if it's just excess capacity, again, you're not completely duplicating the footprint or the investment of the core central treatment plant. But by supplementing it with a technology that in this sense can be a little unconventional, but can meet those needs, then it goes into what's the value of that investment. So if it's dollar for dollar, but it takes up less space, it eliminates sewer overflows or basement backups, and it essentially helps you be more responsive to potentially upcoming regulations regarding micropollutants or emerging contaminants of emerging concern, whether that's forever chemicals or something else, pathogens. So the value of that dollar can go further if what you're trying to do is not just duplicate what you've got, but take into account all of the other things that have changed since we first built these treatment plants 100 years ago.
I really love the idea of what you're describing. It's almost to take the term from other sectors that are mildly more digitally advanced and transformed, more mature than the water sector. This idea of a decentralized approach to treatment. Is that where you think we're heading then? So more of a decentralized approach and more of an adaptive, sort of proactive, dynamic approach to be able to support populations?
Absolutely. When we design these systems and we design them to be centrally to have these conveyance systems that bring you to a central location, but the investment is always on that central location and not on that conveyance. This is as much on any utility as it is on the public that they serve, because that conversation has to keep going on. Why are we increasing our ratepayer taxes? Why are we digging up your street? When those conversations come up, but there's not an engagement with the community, it's understandable why communities get frustrated that these rate hikes go up or that these construction projects interrupt their commutes. But having those conversations and understanding why the conveyance system also needs that infrastructure. And if that, or in addition to that, what we also need is to not be relying so heavily on that broken conveyance system and consider at that location that overflows every single time it rains. And there are some combined sewer cities where every single time it rains, there are a few locations that always overflow, or there are a few homes nearby that are always worried about basement backups. And you already have a conveyance infrastructure in that location that would otherwise take it to a centralized location, but miles and miles of infrastructure, then we can consider at that location to serve, maybe not all the time, which is another pro of chemical treatment versus biological. It can stay dormant for long periods of time. And you essentially have a peaker facility in the same way that you do for the electrical grid, where you can consider what a decentralized system looks like. It's either used all the time or just when it's needed, and it can really solve a problem at the location where the problem is occurring. And also gives you an interesting opportunity to have that conversation with the community. Here's what we're doing, or here's a new perspective that we're adding to solve a problem that you have. And some utilities will say, we don't have a whole lot of remote infrastructure. It's harder for us to maintain remote infrastructure. Either we're a small group or it's just not really the right fit. That's fine. It can be excess capacity at the treatment plant. But there's so many ways where having these decentralized locations that take up less space, that can be started up quickly, and can really have that sort of that impact out in the sewer shed in the service area, can go a long way to not just demonstrating a unique perspective and an innovative look at how we deal with a broken conveyance system and how we serve our communities, but also put something in the ground that advances what we understand about how decentralized treatment works, how chemical treatment works. So there's this twofold. But in order to learn about it or iterate on it, we just have to start.
That's it. We just got to start. Just got to start talking about it.
You got to start talking about it. You have some uncomfortable conversations. Put some shovels in the ground.
Yeah. Paige, thank you so much for joining me today. I really appreciate it. It's been such a fascinating conversation, so much to learn from you. So thank you very much.
Thanks for having me, Jack. I really appreciate the questions and I appreciate the conversations. Keep it going.